Okay, so we saw how important it is to check the integrity of the data. We could see how data could be modified in transit, and that's obviously something we should not accept in our system, because if someone can modify the data in transit, even if it's encrypted, that's obviously really bad. So integrity protects data during in transit or at rest or whatever. It protects it from unauthorized modification. So we can validate the data at one point in time is the same as the data at another point in time, whether that's data still on the disk, data that's transferred over a network, anything like that. It's just protecting it from any sort of modifications. As a big warning, you'll have run across integrity in communications or electronics contests already for sure. And this is very different from security and crypto. The reason being in that most other contexts, like communication systems, the corruption or the modification is random changes, so random corruptions. So you'll have like checksums or parity checks or things like that, where if you have a random few number of bit flips, the system can detect that. We don't have random, we have an adversary that's purposely trying to change data on us. So what this means is that an attacker is often able to modify a file using these regular checksums in a way such that they can make it look like it wasn't changed. So if we consider a normal checksum, not a cryptographic checksum or cryptographic integrity check, it's insufficient because an attacker can easily change it. And a common problem is people using these checksums or CRCs or things that are designed to protect against random data and using it in a situation where an adversary can change the data and you have someone that's actually programmatically trying to change your data, not random corruption. So you have to make sure the algorithm is designed for what you need. So as an example, let's say I tell you over the phone. So let's say I'm trying to send you a file and it's a big file. I can't read you the whole thing over the phone. And I'm using the phone because that's our trusted mechanism, right? You can hear my voice. You know what I sound like. So if I tell you over the phone, there's a checksum program, run the program, and the result should be 938229. And you use the same checksum program. We discussed it before. It's a standard that's well known, like this, where you just add up every byte of the file. And in this case, there's basically a variable, right, that's just adding up the ASCII equivalent of whatever the character is, adding it up into a 32-bit number. The number could overflow if this was a really big file. And it just prints it out at the end. So if this print matches, then you're going to think the file was unmodified, right? But this is not a cryptographic checksum example. And as an example, right, we could say in the file, I had this one phrase, I hate Tor, because I really don't like the Tor browser for whatever reason. I'm trying to tell you about that. And so if I have that in the file, the checksum is going to just be the addition of the ASCII values of those letters. So if you go to I, this little ASCII table here says I is 73, space is 32, H, right? So I'm just going through each of these in sequence. H over here is 104, A is 97, and so forth, right? So you just go along and you can get each of those values. And if you add them all up, you'll get 864. So that sequence of letters will have a checksum value of 864. And that's only part of the file, right? The file has a bunch more stuff in it. But if I can replace those letters with something else that has the same addition, the total checksum will be completely unchanged, right? So you would never know that file has been modified. So as an example, if you go through, you can try to find various, phrases that you could replace that with. One I could find pretty quickly here, you could switch I hate Tor into I love Tom. And if you add up the values of I love Tom, it's going to be the same, right? So I could totally change from hating on privacy Tor browsing to loving whoever Tom might be that we both know. And that checksum would pass. So, right, the checksum makes it look like the file is completely unmodified. And we can do this with, CRCs, with other stuff as well. But the point is that, because of the relatively simple algorithm, it is not cryptographically secure. So we need a cryptographic integrity provided by a hash function. And basically, a hash is cryptographically derived from some data that we verify the integrity of. The difference here when we say cryptographically, basically it means it cannot be reversed. So if someone just gives you the hash, you could never figure out what all of the data that went into that. And more importantly, you can't figure out how to change even if you change one single bit of the input data, it should totally change all of the output. So that's kind of the point of the hash algorithm. Examples of hash you might have heard of, is like SHA-1, SHA-2, MD5, and stuff like that. So all of these are secure hash algorithms. We have a collision. So what we'll call a collision, you might have heard about hash collisions. They occur when two data sources produce the same hash. So if you have two different chunks of data, they should produce different hash values. If they produce the same value, then we have a collision. Collisions are always theoretically possible because basically the hashes are much, much smaller than the size of the files themselves, right? So the file's a gigabyte, but the hash is only 32 bytes or something like that. But the point of the hash is that it's infeasible to figure that out. So it's infeasible to calculate if you have 32 bytes, you know what the hash is. The brute force timelines are so long that you'll never get this to work. For SHA-1, so SHA-1 is now kind of considered insecure, in part because in 2017, such a collision was found. This had to use a better than brute force algorithm still, right? So part of the reason this worked is there was an algorithm that was much better than brute force. And it was, 100,000 times faster than brute force. And this, even with this 100,000 times faster than brute force, you can see it still took basically 110 years of, if you considered a single GPU time, right, it would take 110 years. Obviously, they had a lot more GPUs or CPUs to throw at this. So it didn't take 110 years, but it was still a very significant amount of time. I think it was equivalent to like $100,000 worth of compute time. So that's one of the things that you can run into. So what we're going to have to combine is the authentication and the integrity, because integrity relies on the hash of a file, right? So we can make a hash that tells us this file has not been modified. But how do we trust that hash, right? I had the example of sending it over the phone. Obviously, we won't always have such a secure channel. And basically, the hash, right? The hash allows us to send the file over untrusted methods. And the end user confirms that the hash matches, but you need to get that hash to the person, right? And if you have this secure channel, why wouldn't you just send the whole thing over that secure channel, right? I gave the example where the secure channel is more constrained. But in real life, like if we have the internet, right, then how do you make a secure channel out of that? And why wouldn't you just use, the secure internet channel to send everything? So we're going to answer that by looking into the authentication side of this, because basically there's ways that we'll combine authentication to allow us to validate that small chunk of data, the hash, in a much more efficient manner than if we tried to validate the entire file. So it boils down to basically, because of how we can implement some of these things, we actually want to just validate the small hash of the file, and then send the entire file over the potentially less trusted channel, such that we can easily detect the modifications to it. And that'll be the next section that we look at.